Okay, hello, welcome to Math 1610. This is Calculus 1, and the first chapter that we look at is all review stuff, so you may want to fast forward the video in certain areas and work smart, okay? All right, so 1.1 is on graphs and models. Let me make sure that I got the volume working here before I get too carried away. Hello? Yeah, okay. Just want to make sure that's right. I'm going to do a whole lecture and then there's no volume, that sort of thing. If you have any questions, come see me during my office hours. Okay, so the first kind of technique used in graphing equations would be point plotting. Okay? And this is a tried and true method and may seem elementary, but it's always there for you, okay? And the first way we kind of do this is just to make a table. So you either do that in your calculator or do it by hand, okay? Okay, so an example, maybe something like y equals absolute value of x minus 1, okay? So just plain old y equals absolute value of x, we kind of know how to handle. Y equals absolute value of x minus 1, what happens there? That's kind of the, I don't know, maybe the question. So, if we add something in, if we subtract something in, then we should be able to get this. But let's say we didn't know anything about translations, which we'll look at later in this chapter. We'll just make a table, right? And we could do a table for absolute value of x and also a table for absolute value of x minus 1, right? We could do both graphs, why not? Compare and contrast. Okay, so I'm going to go -3, -2. You could use whatever point you want. And then get our y values here. Maybe I shouldn't have written in this column, sorry. Absolute value of x, which is y. If you put in -3 there, you get out what? +3. So it'd be 2, 1, put in 0, absolute value 0, 0, 2, 3. And then if you subtract by 1, you'll get 2, 1, 0, -1, 0, 1, 2. Okay, and then we'll come over here and graph these things and take a look. Some tick marks going. Okay, -3, 3. -3, 1, 2, 3 is right here. -2, 2. -1, 1. And 0, 0. And then 1, 1. 1, 2. Or sorry, 2, 2. And then 3, 3. Okay. So these absolute value figures kind of look like V. Or maybe you think of it as a flight of birds or something like that. Let's do the absolute value of x minus 1, but I'll put it in blue. Okay, so -3, 2, -1, 2, 3, 1, 2. It's right here about. -2, 1. And -1. Sorry, I was reading off the wrong. -2, 1, and then okay, -1, 0, and then 0. I think it's -1. So if I'd made my table a little better, that would have been easier. Sorry about that. Yeah, that one goes there. And then 0 goes with -1. Okay, and then 1 goes with 0, and then 2 goes to 1, and then 3 goes to 2. Okay, so at the end of the day, and if I had drawn it a little better, it would be easier to tell what's going on there. We have the same graph, it's just shifted down by 1. Okay, and that's kind of what happens, and we'll talk about that later, where if you have a function, say y equals f of x, and you add something or subtract something to the outside, it's going to go up or down depending on the value of that c sitting right there. Okay, so in this case it was negative, so we shifted down by 1. Okay. So point plotting, right? Maybe you didn't even know what the absolute value function looked like. You could have used point plotting to figure that out kind of quickly, maybe even quicker than you could open up your laptop and go on to Desmos, right? Okay. So anyways, let's carry on then. So what are some other things you could do besides making a table? Well, you can find the x and y intercepts. Okay, so let's just make this a new section, x, y intercepts. And, the x-intercepts, so let's say I have this graph. The x-intercepts are the places where the graph hits the x-axis. So first, x-intercept, that's where your x is set to be, well, you're letting y equal 0, right? So y is 0, and then you just have some letter there for the intercepts. Okay, secondly then are the y-intercepts. Maybe put these in a different color, right? So secondly, the y-intercepts, and these are the places where the x coordinate is 0. So maybe some other letter there. Okay. And on the picture, the x-intercept and the y-intercept is at 0, 0. There's one there at 0, 0. Okay. Right. So the book is going to take you through some problems, and they're generally a little harder than what you saw maybe in basic algebra. So for example, we have something like y squared equals x cubed minus 4x. Okay. Okay, so this thing is actually not a function. We'll talk about how to identify functions versus non-functions later, but it's not a function, and it's not something we're familiar with. You know, it's not the equation of a line, it's not a parabola. Who knows, right? But we can get the intercepts. So let's say the x-intercept, and for that you let y equal 0, right? So you plug y into this equation here, and you're going to get 0 squared is 0. Equals x cubed minus 4x. Okay. And then you just solve that equation. So you factor it using all the methods I learned in previous classes. And it looks like we have 3 intercepts. So setting each part equal to 0, I have x is 0, x is 2, and then x is negative 2. Right? So intercept 0, 0, intercept 2, 0, and then an intercept at negative 2, 0. Okay, y-intercepts. So for the y-intercept, you let x equal 0, right? So I just put x wherever, 0 wherever I see x, and I have 0 cubed is 0, minus 4 times 0 is 0, 0 minus 0 is 0. So what number squared is equal to 0? There's only one possibility there, and that's just 0. I mean, you could literally take the square root on both sides, and you'll get y equals 0 if you wish. Okay, so that the only y-intercept is 0, 0. Okay, so we may have no idea what it looks like, but we can find kind of these points on the x and y axis where the graph hits the axes. Okay, okay, let's look at another example, maybe another one. It's kind of more complicated than usual. Okay, so let's take a look at this guy, right? The x-intercept, we let y equal 0. So we have x squared plus 3x all over 3x plus 1 and parentheses squared. Okay. This is a rational equation, and if you remember in rational equations, you kind of have to worry about restricted values. So here, 3x plus 1 can't be 0. We don't want that to be 0, so we find where that happens by solving this equation. Okay, so if our solution to that equation is negative 1/3, so we have to throw that out. That won't work, so it won't be an x-intercept. The function won't be defined there. Okay, so let's go ahead and solve. So how do we solve this? Well, we multiply both sides by the denominator, 3x plus 1 squared. In other words, you set the numerator equal to 0, right? For the restrictions, you set the denominator equal to 0. To solve, you set the numerator equal to 0. Okay, so solve that thing. It's quadratic, so I'm going to factor it. And then set each part equal to 0. So either x is 0 or x plus 3 is equal to 0. In other words, either x is 0 or x is negative 3. So it looks like we're getting two intercepts there, right? 0, 0, and negative 3, 0. And neither x value was negative 1/3. So you always have to check these guys against that restricted value. Okay, so that works and this works. And those are officially points where the graph hits the x-axis. Okay, for the y-intercept, you let x equal 0. Okay, so wherever I see x, so 0 squared plus 3 times 0 is the same as 0 plus 0, which is 0. And that's divided by 3 times 0 plus 1, which is 1, and then square that, that's 1. Okay, 0 divided by 1 is just 0. So our y-intercept is at 0, 0. Okay. So we're kind of browsing through all the different methods for solving equations simultaneously here. So why not look at a radical type, right? Okay, so again, this is something you probably would have a lot of trouble graphing by hand, but you could get information. Okay, this thing tells you a lot. And let's go again after the x and y intercepts. So the x-intercept, you let y equal 0. And the end result in this case is a radical equation. So how do you do radical equations? You isolate the radical part. So I'm going to add this x squared plus 1 to the left-hand side. I'm going to square both sides. And then I'm going to, well, you can isolate the x squared and use the square root property. So let's move the x squared to the, the right-hand side there. And then I will divide both sides by 3. And then I could use the square root property. So x is plus or minus square root of 1/3. Okay, back when we did the radical equation, or sorry, the rational equation, we had to check our solutions. And with radicals, you also have to do some sort of check. It's because extraneous solutions can creep in. So we have to check each one of these. So square root 1/3 first, I'll try. Okay, x equals square root 1/3. And you plug that back into the original equation. Okay, so I'll just underline this guy. You got to plug it back in there. Okay. Okay. So here we go. Whoops, that's not the original equation. I apologize. Not that guy. This guy. Sorry. Sorry. Okay. So I put in square root 1/3 wherever I see x. I get 2 times the square root of 1/3 minus the square root of. Square root 1/3 squared is just 1/3. Plus 1. You square a square root, the square root goes away. So I'll have 2 times the square root of 1/3 is the same thing as the square root of 1 all over the square root of 3. And the square root of 1 is just 1. So I get 2 times 1 all over square root of 3. Minus the square root of 1/3 plus 1 is the same as 1/3 plus 4/3. I think I'm going to scroll down a little bit here for us. Okay. So I have 2 times 1 over square root 3 is the same as 2 over square root 3. And then minus the square root of 5/3. Whoops, is that right? Sorry, the second 1 is the same as 3/3, not 4/3. So the square root of 4/3. Okay. And then clearly square root of 4/3 is the same as the square root of 4 over the square root of 3. And the square root of 4 is 2. Okay, so here 0 is equal to 0. Okay, so that was the first root, and that one works. Okay. We also need to then check the negative square root 1/3. Okay. So again, I put it into the red boxed equation, and I get 0 is 2 times negative square root of 1/3, and then minus the square root of, well, negative square root 1/3 squared is going to be positive 1/3. When you square a negative, it's positive. When you square square root, the square root goes away, so you have 1/3 and then plus 1. And you kind of see this one's going to be different, right? That first term is going to end up being negative 2 all over root 3. And then you get minus the square root of 4/3, which will be, let's not carry the equation in that direction. I always want to kind of move the entire equation down. Okay. So I'll have negative 2 over root 3 minus 2 over root 3. And then that'll be negative 4 all over root 3. And clearly that doesn't work. Okay, so we have to throw out this particular solution. And at the end of the day, there's only one x-intercept. So the only x-intercept is at positive root 1 over 3, comma 0. Okay, long problem there. Y-intercept, now you let x equals 0, so you'll have y equals 2 times 0, which is 0, minus the square root of 0 squared is 0, plus 1 is 1. So y is equal to negative square root of 1 is 1, so negative 1. Okay. What else can we kind of get from the equation that would help us in our graphing? Well, symmetry. Okay. And there's 3 main types of symmetry we'll take a look at. There's going to be y-axis symmetry, which we usually see with the parabola type. And basically, if you have this point xy, you'll also have the point negative x comma y, right? In other words, y-axis symmetry. For x-axis symmetry, if you have the point xy on the graph, so we'll take a sideways facing parabola, you'll also have the point negative x comma y. Oh, oops, sorry, not. You'll also have the point x comma negative y. Right? So that's x-axis. Finally, origin symmetry, or as they call it, odd symmetry. The y-axis symmetry is even symmetry. We'll talk about that stuff later. Odd symmetry graphs are usually like these cubic types. It goes to the origin. If you have the point x comma y on the graph, you'll also have the corresponding point negative x, negative y. Okay? So that would be origin symmetry. Okay, so to test equations for symmetry types, what you're going to be doing is kind of a substitution and then see if the equation is unchanged. Okay, and the substitution comes directly from these pictures that I've just drawn. For example, y-axis symmetry, if we take a look at this ordered pair over here, what did I say? So I said if xy is on there, negative xy is on there. So if I put in negative x for positive x, it should not change the equation. You should end up with the same equation. If you don't, then it doesn't have that kind of symmetry. Okay, so for y-axis symmetry, what am I doing? I'm going to put negative x in for x. Okay, so for y-axis symmetry, let x be negative x. So I'll have y equals negative x cubed plus negative x. Okay. And that's y equals negative cubed is still negative, so I have negative x cubed and then minus x. And then you compare this to the original equation. Are they the same equations? And is this thing the same as that thing? Right? And in this case, obviously not. This is going to have this first guy here is going to have different ordered pairs than the second guy here, right? It'll have some pairs that are same, but it has to have all the same ordered pairs for it to work. For example, 0, 0 works on both, right? if you plug in x equals 0, you'll get out y equals 0 in both. But a point like 1 is not going to work. So in the first, in this one, your coordinate will be 1 comma -2, right? But if you plug in 1 on the second one, you're going to get 1 comma +2. Okay? So they don't have the same ordered pair, they don't have the same y coordinate for all the same x coordinates, and so the graphs are going to be different. Okay, so in this case, no, it does not have y-axis symmetry. What about x-axis symmetry? So in this case, looking at the picture, I'm going to be replacing y with -y. Okay, so I plug -y in for y and see if I get the same equation back. And of course I don't, right? It just turns out to be, if I multiply both sides by -1, I'll have the same as the thingamajig that I got in the y-axis case. So no again. And then finally, origin symmetry. In this case, you're letting x be -x and y be -y. Okay. Okay. So I'll have -y equals -x cubed plus -1, or -x, sorry. Okay. If you clean it up a bit, you'll have -y is -x cubed minus x, multiply both sides by -1, and you get y is x cubed plus x, which is, in this case, the original equation, so therefore it does have that kind of symmetry. Okay. Okay. So now that we have the symmetry, we can go ahead and use that in order to graph expressions. So in this section, we'll use symmetry and the intercepts to graph. Okay, so we'll look at another example. It's similar to the one we just did. So y is x cubed minus 4x. So this is some sort of cubic. And if you study polynomials and you've done it in depth, if the degree of leading term is odd, then it tells you what kind of form it has. It's either like this, or it's like this. Okay. With regards to its end behavior. If the leading coefficient is positive, it's the first form. Okay. If the leading coefficient is negative, it's the second form. Okay, okay, so we already kind of know a little bit about this graph then. We know it's going to be of that first form that I did with the a greater than 0. Okay. So we know that from, this is pre-calc. Okay, what else can we do then? So we can get the intercepts. So the x-intercept, we let y be 0. And solve. Okay, so we get those 3 intercepts. We can get the y-intercept, right? So for the y-intercept, you let x be 0. And then we could go and get the symmetry type. So y-axis, we let, from y-axis symmetry, we're going to let x be -x, right? So we'll have y equals -x cubed minus 4 times -x. So y is -x cubed plus 4x. And that is not the same as the original. Okay, so new on that. X-axis symmetry, you let y be -y. And again, we kind of run into the same issue. If you try to get the original equation by multiplying both sides by -1, you'll get -x cubed plus 4x, which doesn't work. try origin symmetry. Maybe there's some hope there, right? So this time replacing both x and y with negative x and negative y. Okay. Again, multiply both sides by -1, and I end up with y is x cubed minus 4x, which is the same as the original, so it has the origin symmetry. Okay, so a lot of information there. Now we can go to the graph and kind of get a drawing going. Okay, so 0, 0, 1, 2, 0, -1, 2, 0. And origin symmetry. So we know it's going to come in from the bottom, and that's from pre-calculus above to the left. Okay, that's telling me I need to come in from the bottom, and then it's going to go through that intercept and come up, and then come back down and go through this intercept. And then it's origin symmetry, so it's going to kind of have this, the shape of let's call this hump 1 and hump 2 are going to be the same. Okay, the same shape, except one's upside down. And then it's just going to come out and go back up. Okay? So you can get a pretty good picture just by figuring out the x-intercept, y-intercept, and its symmetry. Okay, you do some graphing in calculus. There's a section on applications of what we'll call later the derivative, and we use the derivative and its properties in order to get a really accurate picture of the graph. So basically you're not going to need the calculator anymore to do the graphing for you. Sometimes the calculator would be a little misleading, right? Maybe it's not zoomed in correctly, you're not seeing the right part of the graph you need. You could use calculus to figure out which is the important part. You know, what do you need to look at? Okay, anyways, the last section here is on finding intersection points. Okay. Basically solving systems of equations. So let me say finding solutions to systems. Okay, so 58 these are problems from the book. I don't have the numbers on me, so I'm just going to call them examples. But they are in the book. It's just they change the book every 2 nanoseconds to force everyone to buy a new book. We all know that. So these are problems probably in the new book, but probably from an older edition that I use. Okay, so anyways, we want to solve this system of equations. In this case, there's several methods. You probably learned there's like the substitution method and the addition method. For the substitution method, you'll solve for one of the variables and then substitute that expression into the other equation. So we could try that. So let's say 3x, take this guy, minus 2y is -4. I guess we could solve for x. So 3x is 2y minus 4, and then divide by 3. Okay. And then we substitute that expression into the unused equation. Okay. You can't substitute it back into the same equation or you'll get infinite solutions. Right. Okay, so I have 4 times x, which is 2y minus 4 over 3, okay, plus 2y equals -10. Okay. And then I want to multiply, so this will be 8y minus 16 over 3. I need a common denominator, so 2y over 1 is the same as, if I multiply top and bottom by 3, 6y over 3. On the other side I have -10. And what else? I can kind of butterfly this character, and I'll have 8y over 3 minus 16 over 3 plus 6y over 3 is -10. Combine like terms, so 8, 9, 10, 11, 12, 13, 14y over 3. Move the negative 16 thirds to the other side, and find a common denominator, so that would be negative 30 thirds plus 16 thirds. Probably an easier way to have done this, right? Equals, what is, negative 14 thirds. Oh, and it works out kind of nice. So y is negative 1. Just multiply both sides by 3/14. Okay, once you get that answer, take it and substitute it back into the expression for the other variable. She'll have 2 times negative 1 minus 4 over 3. Which would be negative 2 minus 4 is negative 6 over 3, which is negative 2. So my solution to that system is negative 2, negative 1. So was there an easier way? You'll be asking yourself that a lot as you go through, if you keep taking a lot of math classes. You know, is there an easier way? Is there an easier way? Is there a way I can do it, you know, quicker so I can go home and go to sleep, right? Yeah, in this case there was. So if you take a look at the system, 3x minus 2y is negative 4, and 4x plus 2y is negative 10. You can do the addition method. If you add column-wise, you'll get 7x, then 2y and negative 2y cancel, and then negative 14 on the other side, divided by 7, and you get negative 2, and then you can plop that back into either equation with both unknowns. And you got your solution a little bit quicker, negative 2, negative 1. Okay, so those are, hopefully you've done those before. Maybe something you've not done as much are solutions to nonlinear systems. Okay. So here we have a circle, and here's a straight line. So we could have 0, 1, or 2 solutions. Okay. I'll use the substitution method, so I'm going to solve the second equation for y. Then I'm going to substitute that into the equation of the circle. So I have x squared plus 3x plus 15 equals 25 squared. So that's x squared. I have to FOIL. 9x squared plus 45 plus 45 is 90x. Plus 15 squared is 225 plus 25. So that's 10x squared plus 90x. Move the 25 over, plus 200. You can multiply both sides by 1/10. And you get x squared plus 9x plus 20 equals 0. Then we can factor that. Okay, what numbers multiply together give you 20, but add the 9? 5 and 4. And then set each part equal to 0. And then get the corresponding y coordinate. So y will be 3 times negative 5 plus 15, which is negative 15 plus 15, which is 0. And then over here, y is 3 times negative 4 plus 15, 12 plus 15, which is 3. Okay, so our ordered pairs, negative 5, 0. And the other potential solution, negative 4, 3. I like to check my answers when it goes nonlinear, just in case I did something crazy I wasn't aware of. So negative 5, 0, does it work in both equations? Right? Does it work in both of these equations right here? Right? So negative 5 squared is 25 plus 0 squared is 25. Is that 25? Yeah, that works. Negative 5 times negative 3 is positive 15, plus 0 is 15. That works. So I'm just checking them in my head. 16 plus 9 is 25, and then 12 plus 3 is 15. So they both work, and those will be my, that's my solution set, they would say. Okay. Okay, I think that does it kind of for the big and the small of this section. Let me zip into WebAssign and see if there's anything crazy going on there. There's always something weird that I did not. I mean, I handpicked all the questions, so you should be able to do all of them, but let me just take a look in case there's something maybe I feel that I should take a little more time with. Okay, you could do that one. You can do that, point plotting. Sketch a graph of this thing by point plotting. Can you do that? Let's look at number 3 real quick. So 1 over x minus 7, they want you to graph the thing. Okay. So y equals 1 over x minus 7. Okay, this guy has an asymptote when its denominator is equal to 0. So if you take x minus 7, set it equal to 0, x equals positive 7. So at positive 7, it's going to have an asymptote 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 7 here, and it's going to look like this. Okay. You can kind of do a number line below it and talk about the function f of x. Is it above 0 or is it below 0? Okay, so this is kind of a number line for f of x. So let's take a look at that, right? So where is 1 all over x minus 7 equal to 0? And then we want to kind of do test values to figure out. So yeah, so we do a test value TV for test value and get the sign, and then there's like a conclusion. Okay, so test value in this interval all the way up to 7. Let's say x is 0. Okay, when x is 0, you plug x0 into the function here. You get negative 1/7, right? So that's a point. 0, negative 1/7. So it'd be about right here. The conclusion is that in this interval, it's negative. It's below the x-axis. Okay. So it's, I'll just put like a negative here. And if you do some more test values, it's going to look like this. Okay. X equals 8. So I want to know if it's above or below the axis here. So I put 8 into the original. I get 1. Okay, so it's going to be right here. And so it's positive, which means it's above the x-axis. Okay? And it's going to end up looking like this. Okay? These kind of guys, so functions f of x, which equal 1 all over x, all have the same sort of shape. Okay, they'll kind of look like this. Whoops, and I went the wrong direction on my guy. Sorry. They all have the same shape. They look like this on this side, and then this on the other side. And there's an asymptote for this particular guy at x equals 0. Okay. And then the one we just drew is just a shifted version of the guy I just put in the box. Okay. It's just been shifted over by 7. Hopefully that wasn't too confusing. And it'll make more sense the more of the stuff you do. And I don't know. Okay, so apparently the answer is this guy. This, I can't draw on it, but this one with the key here. Okay, okay, let's see what else. So some hard ones. Test this guy for symmetry. Yeah, let's do that one. XY squared equals negative 9. We always start with y-axis symmetry. You can do it in any order, but so y-axis symmetry, you're letting x be negative x. So you plug in negative x, And clearly it's not the same as the original. You can multiply both sides by -1. No, that is not the same as this. Okay, so new. X-axis symmetry. So you're letting y be negative y, so x times negative y squared equals -9. Negative y squared is y squared. So xy squared is -9. And yes, right, that is the same, so that will work. Origin. So we have negative x times negative y squared is -9. So that won't work, right? So that would be negative x times y squared is -9. So xy squared is 9. And remember, -5 squared is not the same thing as -5 squared. Okay, so you can see when I wrote my negative x squared, I put the negative y squared. I put the negative y in parentheses. You have to show me that in your work. Okay, the first test is written. It's not like online. Just picking A, B, C, or D or whatever. It's written, so I'll need to see your work. And if you're not writing correctly, I need to take off points because it's kind of like not using periods in English. Other people aren't going to understand your work. We need other people to appreciate your work, right? Anyways, -5 squared is 25. This -5 squared is -25. So those are different. Okay, I think that's good enough. We'll stop it there, and I'll see you next time.